Well, thank you for that introduction. I'm the only person on this stage who needs an introduction. As I'm sure you realize, to my left is Jack Schmitt, the lunar module pilot of Apollo 17. To his left is Gerry Griffin, who at that time was a flight director, in fact was the flight director on all of the moonwalks of Apollo 17.
Thank you.
And to Gerry's left is lunar scientist Clive Neal, who is keeping the flame burning for lunar science and lunar exploration.
Thank you.
I think this is going to be fun. It's great to be on stage with these three gentlemen, and I think we're going to have a lot to talk about. I'm going to start with this beautiful photograph that your mission commander, Gene Cernan, took, practically getting on his knees to do it, if I remember correctly, with the camera upside down so that he could capture you, the flag, and the Earth. And I would like to point out that the presence of the flag in that picture underscores the fact that President Kennedy set the nation on a course to carry out what most people thought was science fiction. Most people thought it was impossible. In fact, even some of the people who ran NASA said that they didn't know how they were going to pull it off until they had a chance to catch their breath. At the same time, though...
I never met one of those people.
Well, Chris Kraft in particular, Gerry's boss, Chris Kraft, said to me that when he heard Kennedy's speech, he thought he'd lost his mind. And it was only after a little bit of reflection that he realized, well, we can probably pull this off if we really work at it.
Well, you know, Andy, the Space Task Group under Bob Gilruth, who became the director of the Manned Spacecraft Center, had done a lot of preliminary work.
Right.
And so that group, George Low and Bob Gilruth and people with them, I think felt very confident that they could pull it off.
Right.
And particularly since in 1960, January of 1960, President Eisenhower directed T. Keith Glennon, then director of, administrator of NASA, to begin the development of the one major enabling technology among many, and that's the Saturn V.
Yes.
They didn't call it that then, they called it the Super Booster,
yes.
But that became the Saturn V. So
yes.
Had that not started in 1960, January, making that 1969 landing would have been very, very difficult.
Absolutely, and even as it was, the giant engines on the first stage of the Saturn V almost stopped the show with a problem called combustion instability that took millions of dollars and thousands of man-hours to figure out how to solve. And I love the speech that John Kennedy gave, I think it was the day before he was assassinated, at the medical facility in San Antonio, where he compared Apollo to a story about some Irish boys walking through the fields, and they came to a very high stone wall, and they didn't know how they were going to get over it. And one of them took off his cap and he threw it over the wall. And then the rest of them took off their caps and they threw them over the wall. And they knew that the only way they were going to get their caps back was to climb the wall. And Kennedy said, this nation has thrown its cap over the wall of space. And that's what Apollo was. But at the same time, I want to point out that John Kennedy said nothing about going back to the moon several times and nothing at all about going back with battery-powered lunar rovers and lunar field geologists. So that's a measure of how beautifully, how brilliantly NASA was able to carry out Kennedy's challenge and then have the resources left to do missions like Apollo 15, 16, and 17, which were those extended science expeditions.
Well, one of the little historical facts is that the limitation on the buy of Saturn V's to 15, and that started in the Johnson administration.
How many they could afford to pay for?
Well, that's just what the decision, the budget, that was the decision by the budgeteers. That really, meant that there was going to be end of the program. But at that time, nobody knew how many test flights it was going to take.
Right.
And that would the first landing be successful? Nobody knew that.
Gerry, you must remember that feeling of not knowing how quickly you'd get to the moon, how many times you'd have to redo a mission in order to progress?
Yeah. You know, when we landed on Apollo 11, there was kind of a, I think, a general sigh of relief that, yeah, we could do this. We got them back, got them home. But then we did it 5 more times. We tried 6 more times, but we only didn't make Apollo 13. But every mission we learned something that helped us with the next mission.
Right.
And by the time we got to Jack's flight, Apollo 17, we were hitting on all cylinders. And we had changed our focus, and I can tell you this in the control center, we had changed our focus on 15, 16, and 17 from transportation, just getting them up there and getting them back safely and getting what science we could, to a focus of, we got this transportation system down pretty good now, let's go explore. And that's what we did on 15, 16, and 17. And it culminated in 17, which 3 7+ hours excursions on the moon.
Yes.
Collecting.
That brings me to my next slide, which is the landing site for Apollo 17, the Taurus-Littrow Valley. And in this picture, we have a very interesting marker to show you exactly where Taurus-Littrow is. You see the Apollo 17 Command Service Module. This photograph was taken from the Lunar Module Challenger before Gene Cernan and Jack began their descent to the moon, and you could see their crewmate, Ron Evans, in the mothership there. But say a little bit, Jack.
You know what he was doing? What Ron was doing at that point?
You tell me.
He was doing what we call landmarks tracking.
Tracking.
And that was a technique actually developed prior to Apollo 8, and Jim Lovell did the first tests of landmark tracking, and it was a concept that if we could track craters, the position of which we knew relative to the center of mass of the moon, which we could get from a preceding unmanned mission, the lunar orbiter, then we could narrow the error ellipse, as they called it, for the landing. And Ron is doing that for us, and the difference between our mission and others was that we delayed the update of the lunar module state vector by 1 orbit, which meant that we could shrink that ellipse.
Right.
And actually land in this valley.
State vector means a navigator
yes,
trying
that's
to
right.
determine where they were.
So,
Okay.
so just to
You
give you,
gotta watch the scientists here. You know.
Well,
So
that's
just-
the
just to-
engineering. You guys taught me engineering.
Yeah, that's
You know,
right.
so just to give
it's
you an
too bad-
idea,
It's too bad they didn't have a system of reading engineering, and maybe I could have gotten a degree. You can read the law and go practice law. At least you used to be able to. I don't know if they can anymore.
so just to give you an idea of how far they had progressed by the time of Jack's flight, when Neil Armstrong and Buzz Aldrin landed on the moon, they were 5 miles beyond the place where they had intended to go. On Apollo 12, they narrowed that down to virtually a few dozen yards or 100 yards or so accuracy. And Jack, you want to say anything about the Taurus-Littrow Valley, the goals of the mission?
Well,
why was Taurus-Littrow selected?
Can I first of all tell you about the big mistake I made? You know, after Neil had the problem of landing because of the gravitational field of the moon was not well understood, the decision was made to learn how to do pinpoint landings, and the apparently obvious decision was to land next to a surveyor spacecraft that was already on the moon. It gave everybody a focus. Well, I said, well, I can focus you on a crater over here. You don't have to go to surveyor. Well, fortunately, nobody listened to me because that was exactly the right operational decision to make. Don't you think, Jerry?
Yeah.
Go for the surveyor, and they landed right at, well, within
right on the same rim of the same crater.
Same crater.
So the missions got more and more ambitious, more and more complex. Apollo 15 had landed at the base of a giant mountain range. Apollo 16 had landed in the moon's southern highlands. Why Taurus-Littrow for the final mission?
Okay, I want Clive to back me up on this, but the selection of landing sites was a progressive thing. It depended on what we learned, well, 2 things. 1, operational constraints, and 2, what did we learn from the last landing? And Apollo 11 and 12 were really basically operational missions.
That's right.
We got a tremendous amount of scientific information from the samples collected, and on a 12, the deployment of the Lunar Apollo science package, the ALSEP. But then we started to move a little bit farther afield, and Apollo 13 was targeted to what we call the ejecta blanket, the material that came out of this huge 1,000-kilometer diameter basin called the Imbrium Basin. And the name of that target area was Frau Marl. That was the name of the formation that had been given, the name that had been given to the formation of ejecta from Imbrium. And then, of course, Apollo 13 wasn't able to land, and 14 was retargeted to the same spot.
Same spot.
Now, once we had that kind of confidence behind us, then we could start to think in terms of, okay, let's go to specific science sites that we have the right information to target. And Apollo 15 was targeted to the edge of this Imbrium Basin in a large rill complex, as well as having access to the mountain range around Imbrium Basin. And 16 then was a special mission. We thought we understood what we were going to find at 16, and I think we did, as a matter of fact, Clive. I've talked to you a little bit about that. But that's in retrospect. But for a long time, we didn't know what we found at Apollo 16.
I think the astronauts did. They came back and they were describing, they were told you were expected to find these particular rock types and this, and we're not seeing that.
They thought they were told they'd find lava flows, right?
Yeah, no, they were told they would find very silica-rich lava flows, and Moon isn't. And so they're trained geologists. They're not seasoned geologists. They've gone through the training. They're actually test pilots, I believe. And so
yes,
they're out there saying, no, we're not seeing this. The geologists in the back room tell them, no, you should be seeing this. That's not what we're seeing. We're seeing this. So our training is telling us that this is not what we're supposed to be getting, but this is not what you're telling us it is. So you look at that and you think, well, that training was actually pretty good, because they made those decisions. They haven't gone through we've studied it for X years in college and done field work and PhD, and they actually picked it up, and it shows that the training was really good for science in terms of getting the samples back and understanding what's there.
So Taurus Littrow, correct me if I'm wrong, but did people not think that they were going to find some of the oldest rocks and some of the youngest rocks collected on Apollo?
The targeting of Taurus Littrow for Apollo 17 came after some small debates about whether we ought to go to the far side. I was trying to get us to land in a basin called Tsiolkovsky on the far side. We had all the information we needed. All we needed were communication satellites behind the moon in order to carry it out. And a little group I worked with down there figured that out, got a lot of people in trouble, and like John Llewellyn using the NASA computers when he probably shouldn't have. Nevertheless, Chris Kraft finally caught me in the hall in Building 1 down there and said, "Jack, forget it." And so Taurus Littrow was an obvious choice. It's three-dimensional. The mountains on either side went from 1,600 meters to 21 meters high. It's a narrow valley, only 7 kilometers wide, approximately where we landed at its narrowest point. And the only difficulty was an operational difficulty, and that was the so-called error ellipse, which was very conservative. For the mathematicians, 3 sigma was the error. Very conservative. It was too big. It meant that we had a finite chance of landing on the side of one of these mountains. And that's where this business of landmark tracking and delaying its use to establish our velocity and position in space came in. And by delaying that one orbit, we shrank that down to a 1 kilometer error ellipse, which fit nicely into the valley.
So that's why Ron was doing what he was doing.
That's why Ron was doing what he was doing in that picture. But still, it had a tremendous variety of geological features. It had the Mare basalts, which, and this was as far north and east as we had ever sampled them. It had these massive mountains, presumably a rim created by the Serenitatis Basin Formation event. And it had what appeared to be very young volcanics very young for a lunar thing. We didn't, when we finally sampled them, we found out they were 3.5 billion years old, but still that was the mapping. The mapping looked like these were very young basalts. And also it had an avalanche deposit, which you can see over there off the left-hand mountain, spread like a plume out over the lunar mare.
Right where the biggest cross is. If you look at the bottom of that cross, just to the left of that is the bright tongue that Jack is referring to.
And of course, anytime you're studying these parts of the moon, and particularly these large basins, you're also studying the history of the Earth. And probably the most important scientific return of the Apollo observations, photographs, and samples is that we now understand the very early history of the Earth. A part of Earth history that has been obscured by geological processes down here, and we just didn't really have any idea, just number one, how violent the early history of the Earth was, and two, what kind of materials were there at the time that complex organic molecules were being organized in some still mysterious way to become the precursors to life.
Yeah, Apollo really gave us the perspective, correct me if I'm wrong, that impacts really played a pivotal role in the early evolution of the Earth and life on Earth.
I would only modify that as giant impacts.
Big ones.
Very big ones.
Huge impacts that we can't even imagine.
The largest basin we agree exists on the moon is the South Pole Aitken Basin, largely on the far side of the moon. That is about 2,100 meters, kilometers, 2,500 kilometers in diameter. There is another basin that I and a few other people think existed, called the Procolarum Basin, would be 3,200 kilometers in diameter. And just think about impacts producing features of that scale, not just on the moon, but on Earth.
Yeah.
And more frequently even than on the moon.
If life
So
existed
the
then,
dinosaurs.
Yeah. Well, the dinosaurs found that out.
Yeah.
So at this point, I'd like to show one of my favorite pictures from the entire Apollo program. And it's a picture of Jack walking past the boulders that surround, appropriately enough, the crater Camelot, which was a nod to Kennedy, to John F. Kennedy. And Jack, I want to just quote, we have a poet in Jack Schmitt, as well as a scientist. Jack talked about the experience of taking in the majesty of Taurus Littrow, and he said, the valley of Taurus Littrow is confined by one of the most majestic panoramas within the view and experience of mankind. And he talked about the role of the dark hills across the valley floor, the sweeping slopes of the massifs, the mountains. He said the valley does not have the jagged youthful majesty of the Himalayas or of the valleys of our Rockies or of the glacially symmetrical fjords of the North Countries or even of the now intriguing rifts of Mars. Rather, it has the subdued and ancient majesty of a valley whose origins appear as one with the sun. I want to just ask you, Jack, the experience of actually being there, which you said was beyond anticipation, what is it that the pictures don't show? What does this picture not show that you would say you took away from that first moment when you had a chance taking a panorama to really experience the valley?
It is the photographs and the words that cannot communicate being there. That's the unique part of the human experience. You're here tonight. We were there on the moon. Being there is something you can't transfer to anybody. You can just try to describe it. And believe me, I tried to simulate everything that I could about being on the moon, and both in putting together the training program for the astronauts, and also just thinking about it myself. But nothing takes the place of being there. Mm-hmm. Whether you're standing on the rim of the Grand Canyon for the first time, whether it's seeing your first child born, or any child born, all of these things require the presence, the being there of humans, and that's the thing you can't That's why you've got to get everybody up on the moon someday.
I'm with you on that. Clive, let's get on it.
Let's
So, Jack,
get busy. Yeah.
you had, and you and I talked about this many years ago, but you explained to me that you had been, as a field geologist here on Earth, you had been in conditions that felt much more dangerous. You'd been climbing alone in Norway, and one time you had an infected foot. Now, you weren't alone that time, but you'd never, the thing that made being on the moon different as a field geologist was the immense time pressure.
Well, there are two things. One, time pressure. Dick Gordon, the command module pilot on Apollo 12, and my training partner as a backup crewman on Apollo 15, always said, Jack, you'll learn that time is relentless. Well, it is relentless for all of us, believe me. I'm noticing that more and more. But it is in space, maybe in spades. The other thing is that when you're alone in the field, as a field geologist, you don't have people like Gerry Griffin and John Llewellyn and all these guys managing the risk of being there. The risks exist, and they'll always exist. The risks of deep space are never going to go away. And what we learned to do with Apollo was to manage those risks.
Yeah.
And that has to continue, and Gerry can talk to that much more.
Yeah, Gerry, were you more worried about Jack than Jack was worried about himself?
No, I don't think so.
I think I blew that one. What do you think?
Yeah, I think you did.
Well, I tell you, by the time we got to 17 particularly, that backpack and spacesuit combination, it was like a little spacecraft that he was living in and walking. And that thing turned out to be so robust. I thought it was going to be this little delicate thing that every time we turned around, something would be going wrong with it, or never happened. That little thing, that backpack, it had water, it had coolant, it had power, it had communications.
So the moment in EVA-1, when Jack was trying to help Gene get the deep core out, and I don't know if you guys have seen this video, but go look on YouTube, look for Jack Schmitt, deep core extraction. He launches himself literally parallel to the surface and comes straight down, and he did it several times.
Well,
were you worried when you were watching that?
Yeah. In fact, EVAs, extravehicular activity, it's when you go outside the spacecraft you're not living on ship supply anymore. You got in this case, you had your own backpack.
At one time we called them excursions. That sounded a little bit too nice.
But you know, the thing that Mission Control and the astronauts were a team. We had a lot more data than they had. We could look way down into the system's voltages, temperatures, pressures, etc. And then we had this giant pyramid below us of the contractors that built the hardware. They were online. If we ran into a problem, we could have them run a test for us right quick. We did that through, not out of the control room, the front room, but we did it out of the back room. So we had this vast amount of data we could see. They were the only ones that could do anything, though, with the spacecraft or the suit or whatever. So it took this combination, and this is what the point I wanted to make, and Clive hit on it a little bit a while ago. I really do think the secret of success of Apollo was training and simulation primarily. For the 1960s, we had as high fidelity simulation capability as you can imagine. In fact, it was so good. When these guys were in a simulator, they were in one building on the center, and we were in the control center. We literally wired between the two. There was no wireless then. We wired between the two to get the data out of that simulator into the control center. The control center, it looked just like a real flight to us.
But
and we sweated. You could feel your hands getting a little nervous. And we had some guys called simulation supervisors.
Sim soup.
They
were evil.
Diabolical. They could throw you a problem, and we'd fix it. So they'd throw you another problem, and we'd fix it. then they'd throw you two problems. They could bring us to our knees eventually, but those guys were so good at finding weaknesses in our mission rules and our procedures that's where I think we made Apollo by being ready to go when we left. We were ready.
Okay, so
Just
I'm sorry.
a second, I've got to follow up on
Yeah.
that. I sort of lived in mission control a lot.
He was just a flight controller that happened to be an astronaut.
And I was on the SimSoups team once for an Apollo 11 simulation of an EVA. And we finally, and Gene Kranz was the flight director on that particular sim. And we finally got enough problems in the lunar module with Neal, quote unquote, and Buzz out on the surface that Kranz says, "Get them back in." And the then director of science at NASA was participating in mission control in the sim. He said, "Well, but what about the rock box?" And Kranz said, "Blank the rock box." I mean, tell you, the emotions in that center were just unbelievable. And,
Can I say one more point?
Had not heard that
Just
story,
one
Jack.
more.
That's
It was same in the control center. It was same with the astronauts, really with the astronauts. The astronauts knew the risk. They had signed up for that when they signed up for the program. They knew that their life was on the line. They could accept that. What they couldn't accept is screwing up in front of their peers and making a mistake. That really, and it pushed the flight controllers the same way. Don't make a mistake.
okay, so Jack's on the moon. Jack and Gene are on the moon, but you're in the flight director's chair. And let me just show you a couple of pictures that'll relate to the next question I want to ask you guys.
wait a minute. You can't leave that picture.
What's that?
You can't leave that picture.
I can't?
No.
I have good ones to
Because
follow.
that's a ring of basalt lava.
Oh, I love those boulders.
Around a crater.
I love those
And
boulders.
this guy
but-
knows more about
Well,
basalt
we'll get to
lava.
him, I promise. I promise.
I got the best
But
seat in the house, so I'm fine.
But, so, let me just show you two pictures. So, here is Jack on EVA 1. First day, he's only a little dirty, but notice that he is letting the rake rest on his right hand because your hands get so tired from the pressure of the suit. Here we are, 2 days later, he's up on the side of a lunar mountain, hundreds of feet up. He's folding sample bags. He's getting tired. He's exploring what turned out to be one of the most interesting things on the moon. But anyway, after they get done with this, they ask for an extension. And here's Gerry in his flight director mode. And you said no because you were afraid that they were getting too tired.
There were two problems. Actually, in preparing for this, I went back and looked at the EVAs just for fun, the transcripts. There actually was two problems. Yeah, they were getting tired, and by their own admission, they acknowledged in that third EVA, they were getting, that third EVA was tough. It was rugged. You had, as I recall, you had a long transit time on EVA 2 on the rover where you kind of relaxed.
Yeah, you warm up.
They had nothing like that on that third EVA. They were quick stops, and they were tired.
And that was a 20-degree slope that boulder.
And working on that slope and all that, it was tiring.
And the lunar module was 3.5 miles away.
Yeah.
If the rover broke down, you guys would have to walk back.
Here's the other thing. You may have forgotten this. I constantly was asking on the consumables on the backpack, how much oxygen, how much battery power, particularly those two.
Cooling water.
And yeah, I could let them get a little hot. They froze to death most of the time anyway because they had this coolant suit that
water-cooled underwear.
It
Worked
froze them. Even on the minimum setting, you guys said it was cold. But the other thing is that I had asked for a status, and I got a report, and this was when you were at Station 9, which was the last station we went to. It was supposed to be 10, one more, but we cut it out, that the oxygen would run out somewhere between 7 hours and 15 minutes and 7 hours and 30 minutes. So we started looking ahead, and because he made my case here, the clock seems like it's running at about 1.5 times speed. And when I looked at the whole thing, I could say, we can't do that last site. We're going to have to get back. And so I said, no, we're not going to extend, and we're not going to extend and guess what? This is the thing I looked at. When they got back in the lunar module, I don't know how much oxygen was left, but we got back at 7 hours, 15 minutes, and 8 seconds is when you close the door. So I knew it was going to take longer than it always does. And by the way, we considered at one time trying to run simulations with a fast clock, but we fiddled with it a little bit and decided it was too unreal to. But time just passes so fast when it's such a precious commodity, and that's what these guys had, was this precious commodity.
And you look at this boulder.
The scientists wanted more.
Look at how big that boulder is, and you can't even see most of it in this picture. But Jack, you had about an hour at that boulder, and it still probably wasn't enough.
Oh, you never have enough time. The best indication of that, of course, was at Station 4, the Shorty crater.
So here is what you saw. Not a very good representation of it, but you found, well, you say what you found.
Well, this was, I was walking up to the rim of the crater. The general procedure we had was that the commander would be doing the housekeeping around the rover, dusting the reflective surfaces and things like that. And I would do reconnaissance to see what might be the best sampling sites. And I was moving up to the rim of this crater we call Shorty, about 100 meters in diameter. And and as I walked up there, I noticed that there was an orangish tint to the soil at the rim of the crater. And I hesitated for a moment because just about an hour earlier, I had started to sample an orange reflection off the lunar rover.
The orange foil on the rover.
Yeah, and you'll hear that in the transcript. I'd say, wait a minute. But and then as soon as I realized it was truly something special, I started to dig the trench that you see here in this picture.
You're going to show a better version of this.
And the problem is that printing these Hasselblad the Extrachrome 360 film has not been really worked out within NASA. And so a good friend of mine, Ron Wells, a retired astronomer from Berkeley, and I started working, is there some way in which we can bring out what I actually saw? And I described in the transcript. For one thing, I had an international orange decal on my camera. The camera was right here. And I could, of course, I could see it directly, and with the sun directly behind me, the color of that was the same color as my decal, and I said that, plus a few other things about the color. So we'll see in a minute what the result of our efforts was to finally show people what that color was.
Let's bring Clive into the
by the way, that turned out to be volcanic ash. I didn't know it at the time. I thought it might be an alteration of some kind, water causing iron oxidation and things. That because from
a volcanic vent,
vent of some kind. But it turned out to be volcanic ash and a very, very important sampling site.
So, Clive, tell us about not only this, but anything else you want to comment on that we've just been looking at from a 21st century perspective and the work that Jack did on the moon and what we've learned.
Well, let's acknowledge the gift that keeps on giving, which is the samples that the astronauts actually collected and brought back. And so let's fast forward. This was collected in December 1972. Let's fast forward to 2008. So we've got 36 years on the clock. We've had these samples in Johnson Space Center. We've kept them as pristine as we can. And in 2008, we finally figured out that they contain water. And
this sample in particular.
This sample in particular. And so the moon is bone dry. This was what I learned when I was a student, that there are no volatiles in or around the moon, but They brought back basalts with bubbles in them. Sorry, basalts. It's my northern Indiana accent. And, they got holes in them which are bubbles. So there are volatiles within the moon, but this was the first definitive evidence. Because we kept those samples safe and pristine, still available for analysis, that showed that there's water inside the moon. And then more orbital missions show there's water at the poles. And then the samples, the regolith that brought back, you heat up the regolith in a vacuum,
The soil.
and water,
Yeah.
the soil.
The regular soil.
Yeah, and water drips out the bottom, and it's due to solar wind hydrogen being implanted in the soil. It reacts with the oxides in the minerals, and you get water out of it. So the moon has 3 reservoirs of water, and these samples represent some of the first ones. And the other thing, one of my students found, that you look at these samples, they're millimeter, sub-millimeter spheres.
Glass beads, right?
Glass beads. And my student comes in one day, he's been hand-picking these. He'd done something wrong. This is purgatory when you're hand-picking samples, very small. And
We've all done it.
And he said, I found a Pele's tear.
What's that?
This is like a teardrop shape in one of the glasses. And what this is indicating is that when you explode into a vacuum, you get spheres. But there wasn't a complete vacuum, that there was some sort of atmosphere on the moon at that time that this particular sample fell through to form.
So just to set the stage, the orange soil that Jack found originated as what's called a fire fountain. So imagine molten rock spraying into the lunar sky billions of years ago. And as it falls back down, it cools very quickly, too cool to form crystals, and instead forms tiny glass beads.
Tiny glass beads. And if it falls through an atmosphere, and you see this on Hawaii when you get the volcanic bombs coming out, and they come down, and they've got a sort of blunt end and a tail behind them. This is on a very, very micro scale. A Pele's tear is like one of these volcanic bombs. And there have been models that have shown that there must have been at least some sort of atmosphere on the moon at the time of the peak volcanism. And this is the first evidence that we found that actually supports that modeling.
Certainly a transient atmosphere during the eruption.
During the eruption.
And another piece of that is that not only was there orange soil, but underneath there was black soil.
Black soil.
But identical in composition. And it was black because crystals had begun to grow in the glass.
Yep.
And so you had some of this material staying warm enough to devitrify, is the word, and others got ejected far enough away that they cool very rapidly.
They cool very rapidly, and you get these glasses out there.
What a beautiful counter-argument to this misperception that you hear all the time, that the moon has just been there, done that.
No.
It has not been there, done that. And we're still finding out things about the moon. I like to say that the moon is the crown jewel of the solar system.
I use cornerstone, but crown jewel is grander. So, but if you look at the samples that we know, and now we've now got excellent global data sets from orbit. We
like
now
this
know,
one, like this photograph,
this photograph
of Jack's
from
landing
LRO.
site from the Lunar Reconnaissance Orbiter that is so detailed that you can see the footprints and the rover tracks.
Rover tracks, yes. You can see, and this is, so if somebody says it was staged in Hollywood, it's, but just tell them about the samples. You can't fake those. There are compositions unique to the moon, such as the ones that Jack brought back that we have none of on Earth. And we can't make it in a lab either because that won't give you an old age. But that's if you now combine Apollo with the global data sets, we now know that there are rocks on the moon that we just didn't sample. We know where to go to get them. We now know that there are resources on the moon that we can use to support human life.
Let me go to your next slide, Clive,
Yep.
so you can talk about
All right,
that.
this is a very sort of Zen diagram. It's a Venn diagram. But this is what we found paper just last year. 38% water ice at the lunar poles at the surface. We don't know what abundance it is in or what form it's in, but we know that it's there. Now, we're very good at doing science and we're doing exploration, but now we've got this commerce bit. And if we can get back to the moon to understand what these deposits are, the bits in the middle of the diagram there, these pertain to what you would need to develop a business model to mine the resources, to then bring the commercial sector into the equation when we go back in 5 years, according to the Vice President. So again, but this is something that is different this time, is that we can create jobs on the moon. And at Notre Dame, my goal is, before I retire, when I ask my students, what are you doing after Notre Dame? And they're going to say, oh, I'm going to go work on the moon. That is not science fiction anymore, because we now know that we've got the resources there to bring in the commercial sector, the private industry. Now, NASA can actually seed that. We've got to go prospecting. But this diagram I use a lot because it shows you the data that are critical not only for science and exploration, but also for commercial interests to be able to do this. So this is something I look to the future for, on the basis of the legacy of Apollo, what it has taught us about the moon, and how we can now move forward sustainably and to permanently have a permanent presence on the moon. That's the next step, in my opinion, that we should be pushing for, because we're going to bring the moon into our economic sphere of influence, and we're going to start up a whole new sector of the economy. And it's already starting with the launch companies. It's already starting with the the payload services. NASA has the Commercial Lunar Payload Services program now, where they're contracting out to deliver payloads to the lunar surface. And this is starting big, but the resources that we know are on the moon are going to really expand that, so that we can have the moon as a refueling station to get us to Mars. So water is the oil of the solar system. It's life support, it's radiation protection, and it's liquid oxygen, liquid hydrogen. If only we could build the liquid oxygen and hydrogen engines. Where's my NASA Langley young lady? So this is something that we need to plan for the future, so that we can be out there permanently. And so that's why, listening to the legacy of Apollo, what better legacy than to use the samples that we brought back to understand how to go back there permanently this time.
Bravo, bravo. Well, at this point, I'm going to let Eric change slides on us, because Jack has a few slides that he'd like to show. And I think while he's doing that, let me ask.
Could I tell us?
Go ahead, tell it.
I
was going to tell
I'm gonna
it,
let them
but you go tell it.
I want to tell a story about the orange dirt. When Jack found it, he got
We
all...
normally don't let him use the word dirt, but go ahead.
It's regolith. Anyway, it was stuff. When he got all excited and said, it's orange, it's orange.
Oh, yeah.
And all that. And I'm sitting here, I'm the flight director. I graduated from Texas A&M. And
Show that person out.
that was our primary color is maroon and white. Our adversary is the University of Texas, which was orange and white. So I don't know whether you remembered it, but when we woke them up, the Capcom, at my instruction, which I had lined out, said, we woke them up with music of some kind. And when they woke, kind of got good there, the Capcom said, the flight director would be a lot happier today if you could go out and find some maroon. You remember that?
Yeah, I do.
And, and that's where it ended. And Cernan said something like, "Oh Lord."
Yeah, I just wanted to tell you, I don't think we've shown a picture of the lunar rover yet, except from the overhead.
Yeah.
Right. The overhead. But unfortunately, early in the first excursion, the commander's hammer, which he kept in his pocket, hooked under a fender and broke it off of the rover, okay? And these were dust flaps. They really were dust flaps. They weren't mud flaps, but the same concept applied. And when we drove it the first EVA excursion, well, we were getting covered with dust, and it was obviously was something we needed. Because you get a forward rooster tail in 1/6 gravity, it doesn't go back, it goes forward. It follows the wheel up and then goes forward. And once we were back in the cabin after the first EVA, it was clear that the commander was quite concerned about this. And I kept trying to tell him, I've spent enough time in mission control that they'll have it figured out by morning.
Yeah.
So don't worry about it. Get a good night's sleep. Well, I don't think he listened to me, but by morning, these guys had already figured out how to how to repair that fender. And it worked beautifully throughout the whole, the rest of the mission. It was really fantastic. And that, I just attribute that to why, and not only having participated in such activity, but knowing what was going on in mission control.
A lot of trust, both ways.
Oh, I had complete trust.
A lot of trust. We knew they'd do the right thing in orbit or at the moon. They trusted us to do the right thing for them.
Okay, what I want to spend a little bit of time with Apollo 11. This is Buzz Aldrin and Neil Armstrong sitting mission control. Yours truly off to the left. And I believe, and correct me if I'm wrong, but I believe we're waiting for acquisition of signal from Apollo 8.
8, right.
Yeah.
In this picture.
I think when
And
it went around the moon the first time.
Yeah,
and
this was...
you could have heard a pin drop.
Yeah, that's it, and that's very serious. But I just thought people would like to know that these kind of things were going on, and the crews were assimilating the kind of information that you needed to have in order to work in space and to work with mission control at the time.
See, you're talking about the acquisition of signal after the crucial burn to get back out of lunar orbit and come home.
Well, it could have been either one. I think it was
LOI.
It may have
insertion into
lunar orbit insertion.
Okay.
Because if you overburned, you wouldn't have acquisition of signal.
Yeah, right.
Yeah.
That's the thing. Now, also, in the last few years, I've thought a little bit about if there had been no other mission besides Apollo 11, what would we have learned scientifically? And mainly this is a result of Neil Armstrong's activities. Sample collection, we found out that the Mare basalts, contrary to most expectation among geologists, but not of Harold Urey, Nobel Prize winner, who thought that they'd be old, turned out to be very old. And we got quite a range of samples, even from the Apollo 11. The early solar system history was going to be recorded on the moon. That had been speculated, but we didn't know that. And so we could now integrate that into our thinking about the history, understanding the history of the Earth. The chemical and age and mineral eruptive diversity of the Mare was really remarkable, potentially in basalt units. There were 5 different units identified. There were 9 separate vesicle assemblages. That's these little holes. Each one has, for each rock, has a different assemblage of minerals. And there were 2 varieties of these ashes, these pyroclastic glasses, that we ultimately began to understand after Apollo 17. The sample collection continued with understanding. Very early on, 2 different teams began to speculate from the minerals that were in this soil that the moon had to have had a magma ocean, that at least the outer portion of the moon had to be molten at the time of its creation. And that was an insight nobody had up until that time. And we got that from Apollo 11.
Jack, the lunar magma ocean just sort of revolutionized the way we thought about the moon at that time.
And the other planets.
And since then, it's been applied to Earth as the way that planets, their initial differentiation, or how they form the crust and how they form a core, actually occurs through a magma ocean. It's been applied to Earth, and it's been applied to Mars as well. So the moon is teaching us about not just the moon, but it's given us an insight to the solar system. So that's when he says the crown jewel, it is the crown jewel because it's in our back garden, and we can go find out about our planet and about other planets in the solar system.
And much of the resources that Clive had mentioned earlier are related to the accumulation of solar wind volatiles in the soils of the moon over time. And we're still learning a great deal about it. By the way, one of the reasons the gift keeps giving is because analytical technology keeps advancing. Move along here.
And those of you who don't know,
we deployed a great deal of equipment on the moon. One of the most interesting ones, and still today is one of the best samples we have of the composition of this solar wind, this material coming off the sun.
That's what I was going to say.
That it was a Johannes Geiss out of Switzerland. It was an international experiment on the first Apollo mission. It gave us information about that. We had a seismometer on the first mission and that's another story of how that got there, but as well as a corner reflector for laser experiments from Earth.
Ranging
from Earth.
Still in use today. The only Apollo experiment still being used. So.
And so we found out a lot about the nature of the moon, particularly what we call a high seismic Q, which means it rings like a bell. You hit it with a meteor or a spacecraft or something, and it takes an hour for that energy to keep going around the moon before it finally dissipates.
And why is that an important thing to know about the moon?
Well, it meant that we could then bring it into the future seismometer analysis to understand more about how to analyze that data. We knew it was going to be awfully noisy.
Oh, yeah.
In spite of the fact when you don't hit the moon, it's very quiet. Mm-hmm. So it's a combination of the two.
One of the things about the seismometry is that we found there are 4 different types, and one of them is unknown how it actually occurs, but it's the largest one, and it's only magnitude 5, between 5 and 6. But you've got maximum ground amplitude. We know modern earthquakes, earthquakes, not moonquakes, earthquakes, maybe a minute and a half if you're unlucky. On the moon, minimum 10 minutes, maximum ground motion. So if you have a habitat and you're at an epicenter of a shallow moonquake that is bouncing you around at magnitude 5 for 10 minutes, you get a crack in your habitat, you're going to have a really bad day.
So that's one of the things we learn is that how to design things to take those kind of things into account. And as I mentioned, there's now a very high precision and accurate Earth-Moon distance has been measured. It stopped going.
Oh, no.
Eric, you want to press the button? This isn't.
Yeah. You
better call Mission Control. Yeah.
I think we.
Confidence in me?
Yes, just advance it. No.
There
you
There you
go.
go. Got it.
This is what I wanted you to see. This is what the orange soil really looked like. It exactly matches my description. It matches what I saw. So it really remarkably colorful discovery when we found it.
You know, I'm thinking back to the comments that some people were making before you flew. What's the point of sending a professional geologist? He's going to be in a spacesuit. He's going to have the same limitations of time and mobility that the pilots had. What do you say that you found on the moon that shows the difference you made as a professional scientist on the moon?
I would like to answer that when it's done.
Clive ought to answer that.
Go ahead.
Oh, I'll do it now then. All right. First time I met Jack was at the Apollo 17 workshop in the 90s we had at the Lunar Planetary Institute. And I was an assistant professor at Notre Dame then, and was talking about some work I'd done on Apollo 17 basalts. And I was talking about one particular sample, and I was waxing lyrical, trying to look confident, and his hand goes up. He says, "That's not quite right." I didn't collect it from there. It's more over. Yeah, you need to put it in context with the other ones. And I just went, okay, I'm going to shut up now and just listen. So that's the trained geologist eye on there. I learned so much from just listening. He's been there with the training, and I learned more about those samples in that brief time at that workshop than I did in 30 years of looking at them, because they've been brought back, they're out of context. He put them in context for me because he's the geologist that went there. So that's why geologists are sort of important to have on every mission to maximize the science, not just science, but also exploration potential for resources. Put them in context. And that to me, you want a geologist, that's why, because you're training the next generation, and I still like to think myself as the next generation.
Jack gave us the best of both worlds. remember, his title was Lunar Module Pilot. He had duties other than science, but he had gone through pilot training, the full-up pilot training. He was a pilot of high-performance airplanes. So,
Not to mention a really superb
now, I hate
systems
to blow him
engineer.
up like that,
Not
but
a systems guy on the lunar module systems, which was the
Yeah.
majority of the lunar module pilot's job.
so the science piece was just something that we didn't have in any other crewman that went to the moon. And it probably made sense. Like I said, the emphasis was on transportation early on, get what science you can. And then that changed, and it was, to watch him operate on the moon was different. It was entirely different. And the other thing was, at the end of each EVA, and we'd done this clear back to 11, there was a debriefing done by the commander and the lunar module pilot on the ground, radio to us, kind of a quick summary of what they saw and what they thought. Those used to last about 5 minutes. When we got Jack, they lasted about 30. And he lost us in, basalts and breccias, but those guys in the back room loved it. Those science guys in the back room loved it.
Well, let me put a little broader context, too, that you put experts in their field into any kind of environment, whether it's mission control or test piloting, and you use them for the experience and knowledge that they have in this new context. And being a geologist on the moon was no different than having Neil Armstrong as the commander of the first mission. He had the experience and knowledge and reputation as well of being able to do that job. I would never have been able to do the job that Neil did on that first mission, but
Carrying out the landing.
well, I think I could, but I wouldn't put me in there to do it. No, you put somebody who has shown through their own performance that they can do that job better than anybody else in the world.
Yeah.
And that's what you're trying to, that we have to more and more do that, and we have more. The so-called payload specialists in the shuttle era, they had a variety of experiences and applied those experiences to new problems. Right. And that it's just, space is not going to be any different than the Earth. You try to get the best people you possibly can to do the job at hand.
And as you said to me, your mind is not in a spacesuit. Your mind is not in a spacesuit.
Well, that's what comes with the experience. You have 10 years experience in test piloting. You have 10 years experience in geology, and you use that experience in a new environment. And
Exactly.
There's just no other. That's the best way to do it, and I hope we keep doing it.
Yeah, agreed.
Okay, at this point, why don't we take some questions from the audience, and we'll let Eric take care of that.
Yep, raise your hand. I'll come by with a microphone. We're videotaping and live streaming, so we want to get your question on the video. And before we take questions...
Go ahead, Eric. But while you're thinking about questions, I've got some treats here for the crowd.
Going to throw things at the audience, aren't you?
But before you do that, though, I want to just thank Dr. Schmitt for his assistance in getting us the lunar sample on display in our exhibition. I don't know.
And also for picking up the lunar sample.
And bringing it back, yeah.
Well, that too. But it's amazing what a phone call and an email from Jack to the Johnson Space Center will do. Suddenly we got an overnight FedEx shipment with an Apollo 17 sample. So, and it's on display in the West Gallery if you haven't seen that. So.
Okay, all right. Here's a sample for some of you. You have a lot of confidence in me, don't you? Oh. I don't know that I can reach it all the way back there, but I can give it a shot.
Get him short here.
Be easier in 16G.
His arm will be dead.
not being a geologist or anything even close, I'm just wondering how you discriminated what was samples that came from other sources, such as asteroid impacts from Mars or any other body, from native lunar geology.
The main thing is that we already knew from samples that people like Clive and others had looked at that the amount of material that could be attributed to meteors or asteroid impacts stuff was extremely small. These are hitting at such an extraordinarily high velocity that they literally vaporize, and very little of it is left on the moon. It's lost to space because of 1/6 gravity doesn't hold most of it in a vapor form. There are a few clues. You see some concentrations of an element called iridium and some of its associated elements that we know are higher concentration in certain meteorites. You do see some evidence of that in the samples. But some of the elements that are called siderophile, they're iron-loving minerals, you see some evidence that they have been retained, but not much. And as far as fragments of a meteorite, I'm not sure anybody's ever seen one.
They've found them, but they've had to go through the thin sections of breccias. Now, breccia is a rock that's made up of, it's mashed together through impact, and it's made up of very angular bits of other rocks. But if you look at the matrix, you find little fragments in there, millimeter maybe, that have a very unique composition that are attributed to the impactor. But you have to have the technology and the instrumentation to find it. Looking at a thin section, you can't do it. You have to actually map the elements in the thin section to actually pinpoint these little itty bitty little fragments of the impactor. Because you're coming in some speeds that are impressive.
10
no
to 20
no
north.
atmosphere to slow it down.
Yeah, no atmosphere to slow it down. So it's litho braking all the way. It's just hits it and it vaporizes a lot of rock, including itself.
Yeah.
So,
All right, we have a question over here on your right. Young man.
I would just like to ask, what are your thoughts on future lunar missions?
I think we got to go. That's where we're going.
yeah.
And
Yeah.
I think we got to go there before. Here's a perspective. It's been 50 years since we've sent humans out of low Earth orbit. Getting close.
But how do we make it happen? How do we make it happen? Jerry,
Well, I
you
think-
saw how hard it was the first time.
It's hard. And one of the things that we had in the 60s is we had a bold leadership that decided to set it as a goal. And then we had both sides of the aisle that signed up to it. We had a
Because we had the
Republican
Cold
Senate.
War.
Yeah, we had a Republican Senate and a Democrat House, and the leader and the speaker worked together to
But that was
make
during
things
the
happen.
Cold War. That was a very different time.
there was a threat.
Is it?
Okay, so say that. Explain what you mean.
The geopolitical situation today is probably very comparable.
How so?
China.
Well, it just is. There's competition out there. And
China
very real
probably-
geopolitical competition.
I got to chime in on this one.
But there was a nuclear fear, kind of immediate almost, that I think there was a race.
Yep.
There's no doubt.
Clear cut.
Yeah.
Unfortunately, races aren't sustainable. When competition was on with the Soviets, once we'd won. Okay, now what? And Apollo was finite. So looking at cooperation rather than competition now, and our competition may get it started, but we saw
Right.
there was a signing of an agreement between the European Space Agency and NASA today about cooperation in terms of lunar science.
Right.
I think that knowing a lot of Chinese scientists, they would like cooperation. It's the higher ups, the politics, and I don't do politics at all well. So I think that we've got to think about going back
Sustainably.
and permanently,
Yeah.
so that we build upon the technological achievements of Apollo. I mean, you hold up your cell phone, you say, "Thank you, Apollo," because that led us down the road to miniaturization of electronics, and we've gone down that road quite well. So it's an opportunity to actually expand the economy. It's not NASA's budget is an investment. It's not a drain on the economy. It's an investment in our future. It's an investment in the next generation, like the young man that just asked the question. You want to be on one of those lunar missions, right? I'm too fat. I can't go. So going to need a bigger rocket.
We can work on that.
Yeah.
We have a question towards the back of the room.
Okay. Yeah, I had a question on the vacuum of space. Apparently there's a huge difference between the Earth's pressure and the Moon's pressure, the negative vacuum. How is it that the lunar lander withstood the negative pressure and not exploded outwards?
Great design.
Designed that way.
The pressure actually, if you're into vacuum terminology, the pressure at the surface of the moon is basically that of deep space. It may have varied, as we talked a little while ago, through time, particularly when there were volcanic eruptions, but it's deep space vacuum. And one consequence of that is you really can't build good simulants here on Earth because you can't form them in a vacuum comparable to what you have on the moon with other environmental factors
You're talking
thrown in as well.
about simulating lunar soil?
Simulating lunar soil, the simulants. And now there are certain pieces of the problem that you can do, but not a full simulant. So you need to be planning in the future. This young man could be planning to do in-place experiments so that you learn about what happens in that environment. We don't know everything that happens in that environment. We can speculate, but we don't know. And so these in-place or in-situ experiments are going to be very, very important. The vacuum, though, the design of the spacecraft took advantage of a wide variety of experience in design. I believe the pressure chambers were a big part of that. We have designed a lot of systems and configurations and materials that withstand pressure differences, which is the important thing. What's the difference in pressure? And in fact, working in the deep sea is a lot tougher than working in space, because in space you only have a 1 atmosphere difference. In the deep sea you get to that very quickly.
It's worth pointing out that the metal that protected you and Gene from the vacuum of space while you were on the surface of the moon was very thin stuff, right?
Well, the pressure vessel was a little thicker, but it was only 5 psi too, 5 pounds per square inch. It wasn't even an atmosphere, it was 5 pounds per square inch. So they just designed all ways, both directions, expansion and collapsing in a higher pressure. It was all calculated, and Grumman did a good job. One
of the interesting experiences you have when you open the hatch door, no matter how you depressurize anything, you open a valve, you open the hatch door, and the pressure difference is such that stuff starts to fly out. Some of it is ice, some of it's a piece of bread that you dropped or something like that. It flies out of the hatch.
That's how you clean the module, right?
Well, I think we got rid of some of the dust there.
All right, we have a question at the very back of the room. A young man here.
I have a question about lunar dust. I've heard it has a very noticeable odor. What can you tell me about the smell of lunar dust in your experience?
It's, I think, unanimous. It smells like spent gunpowder. And there's probably a very good reason for that, in that spent gunpowder is really activated carbon, and it hasn't been fully, the surfaces of each individual particles have not been fully compromised by oxygen and nitrogen in our atmosphere, and so it has a unique smell in your nose. And the same happens with the moon. You bring that material into the cabin, and before it gets completely compromised by the atmosphere in the cabin, oxygen and water primarily, and some carbon dioxide, it will have the same smell. It'll activate your sensors in your nose the same way as gunpowder does.
And are you the first recorded case of lunar hay fever?
I'm the first one to admit it, and to actually have enough swelling of my turbinates in my nose, to be a little technical, that it affected my voice a little bit. It eventually went away. By the time we were through on the moon, I had no symptoms of it. However, one of the flight surgeons who was assigned the duty of getting our spacesuits out of our spacecraft had a comparable reaction to the degree he had to stop working.
Was that Carpentier?
Yeah, it was Carpentier.
Bill Carpentier, yeah.
Yeah, so it is an issue, but it's an engineering design issue. It's not a biomedical issue, in my opinion.
When we
you,
go back
you
to
don't
the-
want people to be breathing dust on the moon,
Right.
so you design your systems and your procedures and stuff so you don't have dust to breathe.
And you and Gene both talked, all the astronauts who worked on the moon talked about how much of a nuisance the dust is, and as you just mentioned, it can be a health hazard if you bring it into your environment. How are we going to fix that for future lunar expeditions?
Oh, that's a piece of cake. First of all, you leave the suits outside.
Yeah.
You don't bring them into
Don't
your
bring 'em in.
habitat. The primary vector for dust in the cabin are the suits. Now, another thing you can do is design suits that reject dust, either actively or passively. There are materials that will do that, or you can put a charge. Each lunar dust particle has a negative charge because there are unsatisfied electron bonds on it, for those of you into unsatisfied electron bonds. And
Hands up, who's into it? Come on now.
and so you can use electrostatic forces to reject it, or you can develop materials that will do the same. So I have no doubt that engineers like Gerry are going to figure all of this out. But primarily, you don't bring the suits into your habitat.
Grumman is looking at a descent stage that would actually have a pressurized portion that would be your mudroom, so that you go in and change there and leave the ascent module for sleeping and eating and flying.
Okay, being from Vermont, I understand mudroom.
Mudroom.
Thank you.
Yeah, okay. Well, Kansas City probably understands mudrooms, yeah.
All right, we have a question, maybe hidden by the projector, but right here,
No, I can
midway
see
back.
it.
I can see it.
I thought I read a couple weeks ago.
Hey, did the Royals get to play today? They did? Well, great. How'd they do? 5-3, right? All right. Very
Astros
good.
won.
I'm sorry, baseball is.
All right.
What's
So-
baseball?
Teresa and I spent a couple of weeks ago at spring training, so we're really into this baseball.
Whoa. Did they let you pinch hit?
Oh,
or-
I never tell them I'm there.
Since we're talking baseball, the second Saturday program in April 13th, Daniel Mack, who is head of the Royal Sabermetrics, the Moneyball, will be giving a talk at 11 a.m. That's April 13th. A little plug there for the program.
Good.
So, a couple weeks ago, I thought I read that NASA had actually held back a quantity of samples that have never been analyzed, and they've been waiting all this time for technology to advance
Yep.
before releasing these
Yep.
materials.
Yep.
I'd kind of like to hear somebody talk about that.
We're going to
What-
open them.
I'm sorry, say again?
We're going to open them. We just got funded to do that. In fact, 73001, there we go. There's a rock number nerd sitting here. But this is one that Jack collected, was collected in vacuum on the surface of the moon, was then transferred into another, they put that canister into another vacuum canister, and it has been sealed ever since. So this will give us maybe our first true look at the solar wind content in the regolith, because it's sort of loosely bound, and when you jostle it around and you bring it, it's pretty much gone. So and these are new samples. It's being treated like a new mission, and Jack and I are part of the team that are going to open that sample that he collected.
It's a
It
soil
is the
sample?
Technology that.
It's a core sample.
Yeah, that's
Core
the
sample.
point, to make.
The bottom of a drive tube.
So a core sample that they hit into the ground and pulled out, and now
Yep.
it's been sealed up.
One of the interesting things is that that sample, when it was collected, had a very large thermal gradient
Yeah.
within it. Because the top of the sample, of the core, it's a 70-centimeter core, and the top was exposed to a sunlit lunar surface,
Hot.
and the bottom was basically at a cold trap that exists at about 70, actually about 80 centimeters down. So And that's a minus 20 degrees C versus about 150 degrees C of the gradient. So that in itself is of
I
some
am. I am so excited. I mean, I am so excited. You know? I mean, this is. You know, What can you say?
And this core actually is the core of that avalanche I mentioned in one of the early pictures. And it actually goes down into that avalanche, and the avalanche almost certainly was fluidized as well, because it wouldn't have gone as far as it did unless some gases were helping to suspend it.
So just like an avalanche.
It's like a snow avalanche. Snow avalanches are fluidized because of atmosphere that's mixed up with them. That's why they go so far.
All right, due to the time, let's do one more question. Lon, we'll go to your question here.
Thanks. I think one of the most wonderful things that the Apollo program brought was the photography. The photographs brought it all so special to all of us. So can you comment on some of the challenges of getting these wonderful photographs on the moon?
It turned out it wasn't as great a challenge as one might have thought. Let me start from the beginning. I told some people earlier that the reason we were using Hasselblad cameras was because Alan Shepard bought one in Florida to take on his Mercury flight. And when Victor Hasselblad heard about that, he basically became part of the program with a great deal of his own investment in these cameras. And by the time, of course, we got to the moon, the camera was motorized. It had large magazines and things. And the way we learned to photograph was to use them. On our training trips, this training program that we mentioned earlier that really came into fruition with Apollo 13 meant that we spent about a week a month out on real geological problems, but with all the equipment that we were going to use on that particular mission with us. We weren't in suits or anything, but we had the equipment. It was mounted on our shoulders, and we had communications, and everything was as realistic as we could make it other than not having the suits. But you had this camera here mounted on your chest, and you took pictures. And these pictures, we had other people who would evaluate how well we did, and but basically you learned how to point your chest.
No viewfinder.
And you never thought about it. No viewfinder. And if you ever took it off in order to point it, you just sighted along the edge of the camera. And that was as good as a viewfinder. So the only technical challenge I recall is that I believe it was the first camera, the one that Neil Armstrong was using, and only got one picture. I should have mentioned it. The picture that I had on that graph with all the scientific accomplishments, that was the only picture I think we have of Neil Armstrong on the surface of the moon. He's working with the rock box. But that camera, as I recall, had static electricity sparks along the sprockets.
Oh, really?
Yeah, and on the film was just on the outside edges. It didn't make a lot of difference. But it did develop some static electricity sparks along the sprockets as they moved. And somehow they fixed that. It never occurred. It may have occurred on a couple missions, but that's all.
Let's give our panel a round of applause.
Could I make a...
I know, yeah.
Okay, go ahead.
I know the three of us, and we can all make our own comment, but really want to say how much we appreciate what you have done, what Linda Hall Library does.
Absolutely.
And this is my second visit to actually talk to you folks, and I appreciate it very much. You're just doing a fantastic job.
Hear, hear.
Thank you.
Hear, hear.
I had two things to say. One is to thank Eric and your staff. Boy, they're great to work with.
Absolutely.
And the other thing is Wayne Coon's in the audience.
There he is.
All right.
There he is.
That's a familiar name.
Wayne was a military helicopter pilot for a career. Happened to be the guy that picked up Al Shepard out of the water after the first flight. Got him and his spacecraft. And,
Stand up, Wayne.
Stand up, Wayne.
Stand up.
Stand up.
Great.
I just want to ask one question. Who doesn't remember seeing American astronauts walk on the moon? Who doesn't remember? And don't lie to me now.
Don't lie.
So what's your Apollo moment? Everybody needs an Apollo moment, and I think we're on the right track so that this generation has their Apollo moment. Because I can remember getting dragged out of bed at 4 a.m. in the UK by my dad, and me mumbling, I don't want to do this, and he said, son, this is history. You got to get up and watch this. And that's my Apollo moment. And now, if you'd have told me when I was a few years old, at that time, that I would be sitting on a stage with these three gentlemen, I would have laughed at you. Right? But that's the influence of the Apollo moment. And I really hope, and I really, really hope that the nation gets behind us going back to the moon, but permanently, and going further. Because it is an investment in the future of everyone.
Hear, hear.
Well said.
Thank you for attending tonight's program. Let me just say, the guys have another event to go to. They'll stick around for a couple of minutes, but they do have another event to attend. So thank you again, and be careful out there.
Thank you.